Going on now to topic 3.5, variation and multivariable functions as we start our learn. Now, these are the objectives. You might pause and look through them. As background, we'd like to mention that there are two basic formulas in variation. This is the general formula for direct variation, and sometimes there may be an exponent there. The relationship to what we did earlier in slope-intercept, where k was the slope, now k is referred to as the constant of variation. The one later that we'll see is this formula, y equals k over x. This would be indirect variation. So some background. Now pause as you go on and read this. And there is your direct variation formula. Again, the x sometimes may have an exponent there. All right, let's raise it up and you can finish reading and we'll go on. So in your notes, example 1, Hooke's law says that the force exerted on a spring varies directly. So if you see that and they're saying varies directly, right away you should think of the formula y equals kx. That would be the general form of direct variation. That the spring is stretched. So if a 5-pound weight suspended on a spring scale stretches 2 inches, how far will a 13-pound weight stretch it? And here they give a nice diagram of Hooke's law. And then, of course, the solution. Now, here there is a protocol to follow. One of the things the authors suggest is that you convert that standard form to sort of identify the specifics. So y here will be the force, which is the weight applied, is equal to some constant that'll give you a certain stretching of the spring, and we're calling that distance. Now, in the text, they're leaving it as x. I like to call the x distance. So what information do you have? Well, if a force of 5 is applied, then the distance stretch is 2. So step 1 is modify the formula to designate what you're dealing with, and then substitute the known information into the formula, and then you solve for k. Well, we're just going to divide both sides by 2, and we get 5 halves. Now, the next step is to write, in a sense, what Hooke's law would be, which would be force. We now know what our k value is, 5 halves, and what we don't know, in this case, still is the distance. So now we substitute our new values. A 13-pound weight will produce the distance of what? And then here, we're going to multiply both sides by the reciprocal of 5/2, which is 2/5. Here, all this side cancels out, and we're just left with a d. And then this gives us 26/5, which is our new distance, which in decimal form is 5.2. And that would be our answer. So once again, in direct variation, there's our general formula. Apply knowledge from the example to maybe replace letters. Put the known values into that formula. Solve for the constant of variation. Write the new constant of variation formula. Substitute the new information into it, and that'll give you your answer. And this is the protocol that we follow. And of course, you'll have some to do in practice. Here, they're introducing indirect or inverse would be a synonym for it, variation. And here, the general formula, y equals k over x. And that may have an exponent sometimes. Take a moment, read through this. Now we're going to follow the same protocol that we did for the other. So as we look at example 2 in inverse variation, there's our standard formula. Take a moment to read it over and see if you could come up with some letters that would reflect this formula. Notice that it does have an N here for the X. All right, so Y would be weight of a person. K is our constant of variation. And the X is actually distance squared. All right, let's go down to take a look at the solution. So their substitution is equal to ours. And now the weight is going to be 180. We don't know our constant of variation, but there is the distance from the center of the Earth squared in kilometers. So how do we find what K is? Well, we can just use that cross multiplication technique, where when you have a fraction equal to a fraction, sort of a proportion, just cross multiply. So K, I'll put the K on this side, equals 180 times 63070 squared. And that's what they're getting here. Now, what do? Well, we're going to put, we don't know what the new weight will be, but now we're going to increase the distance somewhat, and it would be then 180. This is our new D value, K value, 6370 squared, divided now by the new distance, which they're saying is this down here, 6379, just a little bit. We're going to put this into our calculator, and then they want us to round to 2 decimal places, and this comes out to be 179.49 pounds. So again, a little further away from the center of the Earth, the person's weight gets less. I've often seen examples where they're talking about on a space flight or in the space station, how much would someone weigh? And then there is a point where you get so far away, you hardly weigh anything. And of course, that's the situation of weightlessness. Now, weight is a measure of this, while mass doesn't change. Weight is a reflection of gravity and then distance, as we see here. Now, our next type of variation is when you start combining things, and this is referred to as joint variation. Now, the general formula for joint variation is this, and they're giving you other background items, so take a moment to pause and read this. All right, so in looking at these, what questions might you want to be able to answer? Well, here we're seeing in joint variation a combination of direct and inverse relationship, while here this is only direct. So keep in mind, in joint variation, there can be combinations of things. All right, let's look at an example. As we look at this example 3 of joint variation, what might you do to write the formula? So take a moment. I'll substitute letters and see what you get. Did you get something like this? Volume. We need our K, and keep in mind K is always in the numerator. The height and the square of the radius. All right, let's go down to see what they have. Now, they put the r squared after the k, but this is satisfactory. Here is some more background variation on multiple variability functions. We looked at this formula already. Take a moment, read it over. And I'll raise it up to get the last line. In example 4, I'll call on the authors to present this. I'm using the video provided by the author.
Hello. In this example, we will be calculating the gravitational attractiveness between the Earth and the Moon. Determine the approximate force of gravitational attraction between the Earth and the Moon. From physics, we know there's a function that calculates the force of gravitational attraction between any two objects that have mass. That function says that the force of attraction between them depends on the mass of the first object, the mass of the second object, and finally the distance between them. And this function is given by a constant times the product of the individual masses divided by the square of the distance in between them. Now, it has been calculated that the mass of the Earth is an astounding 6.0 times 10 to the 24th power kilograms. That's a lot of mass. For the Moon, it's still quite large, but not quite as large as the Earth, of course. But the mass of the moon has also been calculated to be 7.4 times 10 to the 22nd power, and that also is in kilograms. The distance between the Earth and the moon is about 3.8 times 10 to the 8th, and that's measured in meters. Now, this is an average distance because the orbit is not a perfect circle. It's an elliptical motion, but on average, this is how far the moon and the Earth are apart. And that constant in the function has also been calculated to be 6.67 times 10 to the minus 11 Newton cubic meters per square kilogram. Using all of these values, we can now approximate the gravitational attraction between the Earth and the Moon. We're going to use, in the formula, the 6.0 times 10 to the 24th for the mass of the Earth, the 7.4 times 10 to the 22nd for the mass of the Moon, and the 3.8 times 10 to the 8 as the distance in between them, and substitute those values in the appropriate places in the formula. Substituting the value for k, we have 6.67 times 10 to the minus 11. Substituting the mass of the Earth, 6.0 times 10 to the 24th. The mass of the Moon, 7.4 times 10 to the 22nd. And divide all of that by the distance squared, which is 3.8 times 10 to the 8th squared. So now all that we have left to do is to carry out these multiplications and this division. Don't let it scare you that this is using this scientific notation for numbers. Remember, you can multiply things in any order, because multiplication is commutative. So for the numerator, you can multiply the 6.67, the 6, and the 7.4 together, and then you can multiply all those tens with the powers together. Now remember, when we multiply things with the same base, we simply add the exponents. For the denominator, 3.8 times 10 to the 8th, well, you could rewrite that as 3.8 squared times 10 to the 8th squared. So you could do a lot of calculations here, but if you do the 6.67 times 6.0 times 7.4 and divide that by 3.8 squared, you would get 20.509. For all of the powers of 10, let's see, we would have a minus 11, we would have a 24, we would have a 22, and then because of the square in the denominator, we would have to subtract 8 times 2, which is 16. This would give us 20.509 times 10 to the 19th power. Now, this answer isn't quite complete yet because in scientific notation, we want there to be just one value to the left of the decimal point. So we could rewrite this 20.509 as 2.0509 as long as we appropriately change the sign, appropriately change the power on 10. Instead of it being 10 to the 19th power, we now need this to be 10 to the 20th power. Another thing that you might be interested in that is also required to complete this problem is to think about the units. In our problem, the very first constant that we had, that value of k, this was Newton meters squared per square kilogram. The masses of the Earth and Moon were both measured in kilograms. And finally, the distance between the Earth and the Moon was measured in meters. So if you think about it, I'll come over here to the side and rewrite all of these units. We have a Newton meter squared over kilogram squared, a kilogram, and all of that divided by meters, but remember there's a square down there, a meter squared. Look what happens to all of these units. In the numerator, we have a kilogram and a kilogram that cancels with the squared kilograms there. In the numerator, we have a meter squared. In the denominator, we have a meter squared. So those will also cancel. So that tells us that the final units of this gravitational attraction force between the Earth and the Moon is measured in.
I might add the comment here that the gentleman describing this, and it's rather tedious, as you can see, that sometimes there's greater gravitational attraction between the moon and the Earth. And of course, this influences tides. And since we are on close to the sound here, we know that we talk about higher tides due to the position of the moon. And that's relating here to when the moon is closer to the Earth, the tides are stronger. We speak of the spring tides. All right, a little bit of science here. That'll wrap this up, and we'll be working on the practice. I'll take some examples and work them out in detail with you as you prepare for the certify.